So first a little bit about myself. My name is Rob van der Ven. I'm from the Netherlands. I'm an aquaculture engineer, studied at Wageningen University. I worked for a company for a while, and then I decided I could do a better job for myself, so I started my own company, Landing Aquaculture, together with a friend of mine. So I'll have a look at the website and see what we do and stuff. So some of my experience, not everything is related to aquaponics, but the Tropenhaus is a project in Germany. I'll show you some pictures later, which is like a semi-commercial scale. It produces about 10 tons of tilapia and some herbs and tropical fruits. Did a small aquaponics systems on a greenhouse research institute in Spain, in Murcia. And I just recently finished a project in Belgium, the project that Tom was talking about, big fish farm next to a big tomato grower. They're two separate companies, but they're trying to, in the future, find a way that they can work together. I'll also tell a bit more about that. I did about 20 plus research scale systems, so for various kinds of testing feeds or vaccines, and or just in general testing new species and stuff like that. And on top of that, several theoretical designs, so designs that never were actually built because either projects didn't get funding or stuff like that, or did designs for other companies, and other companies did the building and the implementation of that. So what is RAS? RAS is basically, they also call it a life support system. It's basically everything you need to keep your fish alive. As Adrian already explained, the main thing is to supply enough oxygen to your fish. If you supply enough oxygen, you can feed accordingly, your fish will grow. Obviously, if you feed your fish, they will produce waste, and the waste needs to be removed. That's the basic of a RAS system. So, talk a little bit about oxygenation. Oxygenation, to illustrate how important it is, most of the mortality in fish farms is because a lack of oxygen. A pump breaks down, or somebody forgets to open a valve. Always little things, but the fish suffocate because there's no oxygen. And especially if you have high densities of fish, it can go really fast. So in fish farming, there's two main sources of oxygen that we use: either air, which is 21% oxygen, or we use pure oxygen, depending on how intensive your farm is. So, especially if you have high densities of fish, you can get very fast swings. For example, if a pump breaks down, you have a couple of minutes before your fish are running out of oxygen. So very fast swings can cause very fast problems. That's why it's really important to keep an eye on the oxygen at all times. Today at the farm we saw oxygen probes in all the tanks. They were all linked to an alarm system, so as soon as the oxygen goes below a certain level, the farm owner gets a phone call or a text message saying run. And there's different ways to transfer the oxygen into the water, all of them obviously with different areas where they're suitable and different efficiencies. So we'll talk a little bit about them. I won't go into all the pros and cons of all of them. That's all stuff you can find on the internet and do for yourself, or send me an email if you need any advice. So there's a couple of different ways to transfer oxygen or air. You can do it with water that is open to the air, so with no pressure, or you can do it with pressurized systems, so water that is being pumped through pipes is under a pressure, and if it's under a pressure you can generally transfer more oxygen into the water. Some examples of the low head or open to air systems are LHOs, low head oxygenation, cascade columns, which is basically like a waterfall or a series of little waterfalls which break up the water and provide some aeration there. You can use diffusers like you see in the picture there, or surface aerators, which is like the paddle wheels you see often in ponds of like the fountains and stuff like that. Then on the pressurized systems, there's a U-tube, which Daniel explained today. Venturis is basically a system where you make a small, you reduce the size of your water pipes to a relatively small size, and then go back out to a bigger pipe size again, and that sudden expansion in the pipe creates like a like a sucking effect, and that sucks in air. Because of the force of the water, you break the air down into small bubbles, and small bubbles then again release oxygen to the water. The cones, which I showed you on the picture, the cone-shaped thingies, or you can sometimes even do it directly into pipelines. Obviously, there's different costs associated to different pieces of equipment. So it's you'll have to see per application. You'll have to evaluate which one is suitable to your application. Well, another picture of the cones. The next thing, as I said, if you feed the fish, they will shit in the water. The solid waste will increase the BOD and start releasing nutrients to the water, which again provide nutrients for bacteria growth. The bacteria compete with the fish for oxygen, so it's basically you want to get the solids out as fast as possible to make sure that all the resources in the water are available to your fish and not be consumed by bacteria. In general, if you have a lot of sludge in your system, you get pipes that are clogging, the transfer efficiency of oxygen and stuff like that, and the general efficiency of filters goes down. So obviously, in most cases, it's best to take out the sludge as fast as you can. So again, there's various removal mechanisms. There's all kinds of different implementations, but they're all based on the same couple of things. Some of them are based on gravity separation, so sedimentation. Basically, you just wait long enough for all the sludge to sink to the bottom and you take it out. The other one is screening, obviously using a sieve or a drum filter as an example. Foam fractionation, protein skimming is another one. Basically, if like fine dissolved solids, if they get agitated, for example, they're heavily aerated, they will start producing a foam on the water. And the foam is something that you can scoop off relatively easily and that you can use to clean the water as well. The last one is ozonation or oxidation, it should actually say. You can use things like ozone, but also bleach or things like that to oxidize the nutrients, basically to burn them. So some examples of the gravity separation. The sedimentation one is the most simple one, and variations on that are the vortex filter or swirl separators or the radial flows. They all act on the same principle of making like a really steady water flow so that the solids are not disturbed and they will sink to the bottom. Screening, there's different applications of screens. You can use a static screen, which is just a mesh where the solids will get caught. There's parabolic screens, basically in a different orientation. Micro screens, which can be drum filters or disc filters or belt filters. Bead filters or sand filters. I'll show you pictures of all of these so you get an idea. These are bag filters, actually the most simple thing to filter. Just drop the water through a mesh bag. The mesh bag will catch the solids. You can do this with tea towels or anything. But it's generally, they clog very fast and they're difficult to clean. You have to clean them with a power washer or wash them in the washing machine. So it's a lot labor intensive. These are parabolic screens. Basically the water comes out at the top here, flows over this little ledge, drops down on the sieve. You can see it from the side. The water goes through the sieve, so it collects at the bottom, and the sludge stays on top of the screen. And because of the water crashing down on the screen, the sludge will wash down and will go out of there. These are used a lot on like koi ponds and stuff like that. They're quite cheap, but normally they can only remove solids up to a certain size, like 200 microns. And generally we want to reduce or take a bit more of the solids out in fish farming. I think most of you will know this. This is just a simple drum filter. You can see here how it works. Basically, the water flows inside here, inside the drum, and then goes through the mesh. The mesh catches all the solids, and when the mesh gets clogged, there's a sensor that measures it. The drum rotates, and you can see there's a backwash. So, like a pressure jet of water cleans the mesh again, and the waste is collected in this tray through a pipe out to wherever you want to store it or reuse it again. Basically, this, you can see here the red line, water coming in, flowing out here, and it needs to pass through this layer of sand to the sieve at the bottom. Basically, the sand acts as a sieve to catch the solids. Because sand is really fine normally, you get really fine pores in between the sand, so they can filter out a lot of the crap in there. But generally, they need a really high pressure to operate, so they cost more energy. A variation on this is the bead filter. It's actually the other way around. The water comes in at the bottom through here, flows up through the beads, through there, and then gets pumped back to the system. The beads are normally plastic and they're much bigger than the grains of sand. The holes in the middle, in between, therefore, are also bigger, and therefore it's easier for the water to pass through. So less pressure is needed to pump the water through, but they're also a little bit less efficient.
How do you get the sludge out of systems like that?
Sorry?
How do you get the sludge out of systems like that?
Yeah, normally you backwash them, you stop the pump. Either you reverse the flow of the water, so instead of the water flowing down to up, you pump it the other way around, so you basically blow out all the solids. Or in some cases you aerate them, which means that all the beads or all the sand will start moving. That will loosen all the sludge. And then there's a little tap at the bottom, and you just drain the whole filter with all the crap coming out. Depending on how intensive your system is, you might need to do that once a week, or once a day, or even twice a day sometimes. So the next step is about biological filtration. Once you've taken all the solids out, most of the solids out, there will still be a lot of dissolved nutrients in the water. So we use bacteria to break down those nutrients. In general, you're all familiar with ammonia being in there, but there's other compounds in there as well that require removing. A general name for that is BOD, biological oxygen demand, which is like an umbrella term for everything that needs oxygen to be degraded into another compound. So what we try to do is, there's certain strains of bacteria that are efficient at removing the things that we have in the water. We try to promote the growth of those specific bacteria. We do that by giving them the best circumstances, the best temperature, a lot of surface to grow on, making sure the pH is correct and all those kind of things, to make sure that they are really good at removing the things that we want to be removed. There's two ways you can do that. Either you just make like a slurry of the bacteria, especially if you have high concentrations, you can do this. It's basically like a big soup of just bacteria, where the bacteria are just suspended in the water and moved around. For example, is bioflux system, where there's just little flocks of bacteria floating around in the tank and at the same time cleaning or taking up the nutrients. In general, in recirculation systems, what we do is we use fixed growth, so we provide a surface for the bacteria to grow on, which is often a plastic media like we saw today, but it can also be sand or gravel or basically anything with a large surface area where the bacteria can grow on. The water flows past the bacteria, and in the meantime they take up the nutrients. So you can see here an example. I just pulled all the pictures out of internet, so some of the sources might be, or I actually have no idea about the sources, but this gives a good indication. I believe this is 1 month old media. Is it Italian? I think so. And this is 6 months old media. You can see the bacteria growing on there, the color of the media changing because of the bacteria. And you can see even normally you can start a biofilter in more or less 1 month, but you can see the difference between 1 month and 6 months. And even if you do 6 months and a year or 1.5 years, you still see differences. So it generally really takes a long time for a biofilter to be completely stable and completely mature. But in general, there's quite a thick layer of bacteria on these media, especially on the insides, like in the little crosses. Some other examples. This is a trickling tower, which is basically this whole tower filled with like plastic meshes, where the water trickles down and the mesh provides the surface for the bacteria. The advantage is, at the same time, obviously you can transfer a lot of oxygen into the water. The bacteria are never out of oxygen because there's only a thin layer of water flowing over them, so it's really beneficial for the bacteria to grow. This is an example of a moving bed filter with the media that we saw before. The same principle as Daniel has on his farm, only this one is aerated to keep the media moving. Basically this is done to make sure that, one, there's enough oxygen for the bacteria, and two, because you're constantly stirring up all the media, they bump into each other and therefore they shear off like old chunks of biofilm, like old bacteria that are not efficient anymore. They break from the media so that new bacteria get a chance to grow again. Another thing which is important in RAS is to take care of the microbiological population. Basically, very roughly said, there's good bugs and there's bad bugs. You want to promote the good bugs and keep the bad bugs out. So the main thing what you want to do and what you're able to do in a RAS is, because you can control everything that's coming in, you can also make sure there's no pathogens coming in. Obviously you need like really good biosecurity protocols for that. But in general, in theory, you should be able to keep diseases out of the door. If you do get diseases in, there's a couple of ways of treating them before you start using medicines. And some of the things are named here, what you can do. For example, you can use UV irradiation to destroy the bacteria, ozonation, chlorination, membrane filtrations, which is like a really fine filtration, the same as what is used for reverse osmosis. If you take reverse osmosis and you do one step less intensive, you can still remove all the pathogens from the water, but it's really energy intensive. And then there's AOT, Advanced Oxygenation Technologies, which is often a combination of UV and ozonation, because all of these treatments or filtration mechanisms have different effectiveness against different types of pathogens. For example, ozonation is much better against viruses. UV radiation is often better against bacteria.
How does it affect the biofilter?
Sorry?
How does it affect the biofilter?
There is a problem with that. For example, ozonation obviously can harm the bacteria as well. It can even harm the fish because of the residues that are left in the water. But generally you place it at such a place in the system where it's after the biofilter. And then you make sure that whatever residues are there, you destroy them before the water gets to the fish. So there's one point in the system where you sort of nuke the water, and you make sure that the water is back to healthy again before it reaches the fish. But there's always like you can control a lot of it with sensors and stuff, so that you make sure that you never reach or never go over a certain threshold. Basically, these methods reduce the microbial carrying capacity. Another way to do this is to reduce the microbial carrying capacity, which is basically the amount of food available to the microbes. And you do this by removing all the sludge and the nutrients as fast as possible from the system, which you can do, for example, with
I didn't get what is AOT techniques.
AOT is Advanced Oxygenation Technologies.
All right.
Advanced oxidation, yeah. Basically, oxidation is the reaction of a redox reaction of any organic matter. Mm-hmm. Basically, just burning the material, which you can do with UV, which you can do with ozonation, and advanced means in most cases just a combination of different methods, so that you cover all the specific areas where they are effective, and by using multiple you cover the whole range of microbes. So some steps that you can take to intensify the production in a recirculation system, as we discussed before. If you use pure oxygen, you can increase the amount of biomass that you can keep in the system. Well, as a rule of thumb, you can more or less keep 3 times the amount of fish or you can support 3 times the amount of fish with pure oxygen than you could with using normal air. When you start intensifying, you start running into problems with CO2 and more with ammonia and nitrates. So you have to start removing, especially the CO2 actively. And CO2 is a compound that has quite a strong bond with water, so it's quite hard to remove it. You really have to use a lot of air to strip out the CO2. Normal aeration won't be efficient enough. You really need like a CO2 degassing tower, which is basically a trickling tower, and you just suck through about 10 times the amount of air, like a ratio 10:1 air to water, what's going through, and that way you can get most of the CO2 out. But it's always harder. The bond of CO2 with water is stronger than the bond with oxygen. So it's, for example, with aeration, if you supply all your oxygen with air, there will still be CO2 in the water because it's harder to break the bond with water. One of the other steps you can do to increase your intensiveness in RAS is denitrification. Basically, the last product of nitrification, so the breakdown of ammonia, is nitrate, which is normally not harmful to fish unless you get to really high concentrations. Then we use denitrification to break that down again into nitrogen gas. And then the water with the really high nitrate concentration gets safe again, and you can use it again in your system. So you have to use less water to keep the nitrate in your system under control.
Let me know if they are using also the Anamox process, like the same process than the nitrification.
Yeah,
they're using it already.
Yeah, they're using it. They're already in the 80s. They were doing some experiments with it.
In RAS.
Yeah. But they're using it, or trying to use it, but it's still very unpredictable. So they don't use it commercially a lot. But I know there's quite some universities doing trials with it. So some additional factors to basically keep in mind when you're working with RAS, or that are important to consider as well, which we won't have time to go into at all. A very important factor is the fluid dynamics or fluid mechanics, fluid dynamics as well. Basically, your pipework needs to be designed up to for the specific application that you use. You have to think about an energy efficient way to transport over water. It's important to think about fish tank design. How do you make the fish feel happy? Get the optimal water quality. It also can greatly influence the health of the fish. And by thinking about how you design the fish tanks, you can make it, for example, a lot easier to harvest the fish, so you use less labor. Another aspect which we won't go into at all is heating and cooling. We could fill a week with that easily. Obviously in relationship with greenhouses, it becomes more important. And obviously all the factors on the water quality, the performance of the fish, needs to be continuously monitored to make sure that the fish are healthy. Because it's such a intensive system and things can go wrong quite fast, it's important to keep an eye on that, to have alarms on a lot of these things. So I wrote here down some important things to keep monitoring once you're running the system. I think that was it. Some features of RAS. Generally, you can recirculate, depending on how intensive your filtration is, between 50 and 99%. 99% is, in most cases, way too expensive, so a lot of people don't choose to do that, but technically it's possible. They can range from really basic systems, and I've seen systems which look like a freaking space shuttle with pipes and buttons and lights everywhere. Obviously, the optimum is always somewhere in the middle. Depends a lot on the money, on the species you're doing, and your location, and your budget, on the environmental regulations and stuff like that. In large scales, RAS is normally competitive in operational expenses. It's competitive with case farms or pond farms. On the same amount of input going in, like feed and labor. But it's more, the investment at the beginning is higher because of all the technology that you need to put in. But it has the potential of producing fish without antibiotics and without diseases, in theory.